Okay, so today we're going to finish up our probability chapter. The next concept we're going to get into is combination. So if you remember, we went over permutations and we said with permutation, order matters. Now we're going to look at combinations. But first, we're going to look at a problem that may sound somewhat familiar. We have a charity benefit and it's attended by 25 people, at which three $50 gift certificates are given as door prizes. Assuming no person receives more than one prize, how many different ways can the gift certificates be awarded? So we can calculate the permutations, right? Which was 25 factorial over 25 minus 3 factorial. But permutations, the order matters. If we were giving away three different values of gift certificates, the order would matter. But since they're all the same, they don't matter. So a way to look at this is this would mean, say we have person A, B, and C. Well, if we gave it to person B, C, A, B, C, B, or B, A, C, or B, C, A, or C, A, B, or C, B, A. We could give it to them in three different orders. But since they're the same prize, the order doesn't matter. So essentially, this is going to give us all six of these as possibilities. So what we need to do is divide that by 6, right? That's 6. There's 6, which if you think about it, is 3 factorial. That makes sense? Because without the 3 factorial, it's going to give us all 6 of these. But they're all the same because the order doesn't matter because it's the same gift certificate to everybody. Doesn't matter who got one first. And then we would calculate this same way. 25 factorial over 22 factorial times 3 factorial. We have 25 times 24 times 23 times 22 factorial. 22 factorial, and this is 3 times 2 times 1. So these would cancel out again. And that's 6. 25 times 24 times 23. Nope, that ain't gonna work. 13,800. Divide that by 6, and we get 2,300. So that's a lot different with the order not mattering. $25 items, combination, 3 at a time. That's the notation, which it'll show on the next page. So if you remember before, we had 25P3. So this is permutation. Order matters. And this is combinations. Order does not matter. So that's the big thing. If the order matters, use permutation formula. If the order doesn't matter, use the combination formula, which will be given to you on the exam. So let's look at the next page. And here it is. So now let's look at another example here. We have a group of 4 students is to be chosen from 35-member class to represent the class on the student council. How many ways can this be done? Does the order matter? No, we're just choosing 4 students. So we start out, N is 35, R is 4. So 35, C4. 35 factorial. 35 minus 4 factorial. 4 factorial. So we have 35 factorial over 31 factorial, 4 factorial. So far, so good? And writing this out, 35 times 34 times 33 times 32 times 31 factorial. There's my 31 factorial, and then 4 factorial is 4
شكرا هذا الجاهل
times 1.
إلين كيفك؟
كيف حالك؟
إلين
شو
أنا
هذا؟
Then we do our math. Well, our 31 factorials cancel out. Then we have 35 times 34 times 33 times 32. 1, 2, 5, 6, 6, 4, 0. Divide that by 24. And we get 52,360. Okay. Now, I think I said this last time, but I'll repeat it. These number of permutations and numbers of combinations will always be a whole number. There'll be no fractions, no decimal. So if you get a decimal, you made an error somewhere. Any questions on that one? You'll see a couple people writing. Okay, so now we have the United States Senate Appropriation Committee consists of 29 members, 15 Republicans and 14 Democrats. The Defense Subcommittee consists of 19 members, 10 Republicans and 9 Democrats. How many different ways can the members of the Defense Subcommittee be chosen from among the 29 senators and the Appropriations Committee? Now this one gets tricky. So you're immediately thinking 19 out of 29, right? But it don't quite work like that, because that would make a combination where there's more than 10 Republicans. So what we have to do is figure out how many ways we can arrange the Republicans. How many different Republican members of the subcommittee are there? So we have 15 Republicans, and we're going to pick 10 of them. And we're looking at this. How many different ways should I choose 10 Republicans out of 15? And again, order does not matter. So we're looking at 15 factorial over 15 minus 10 factorial. Oops. 15 minus 10 factorial, and then 10 factorial, which is 15 factorial over 5 factorial, 10 factorial. Now I'm going to switch it up a little bit here. 15 times 14 times 13 times 12 times 11 times 10 factorial. 5 times 4 times 3 times 2 times 1 times 10 factorial. Everybody see what I did? So now the 10 factorials cancel each other out. This is 120, and this is 360,360. So when I do my division, I end up with 3,003. Now that's just the number of ways I can arrange the Republicans in the subcommittee. Now I have to look at the Democrats as well. So this was Republicans. Now we'll look at Democrats. We have 14 and we're choosing 9. So I have 14, 9. Means 14 factorial over 14 minus 9 factorial, 9 factorial. Gives me 14 factorial over 5 factorial, 9 factorial. Gives me 14 times 13 times 12 times 11 times 10 over 5 times 4, nope, times 10 times 9 factorial. Don't want to forget that. 5 times 4 times 3 times 2 times 1 times 9 factorial. The 9's cancel out, and this comes to 240,240 over 120, which is 2002. So I have two lists. I have this list of 3,003 possible committees for the Republicans. I have a list of 2,002 possible committees for the Democrats. So how many total possible committees do I have? I remember when we had 3 appetizers and 5 main courses. What did we do to figure out how many possible meals? Multiply. So let's multiply. 3,003 times 2,002. And that's a whole lot of subcommittees. And we get 6,012,006 possible different subcommittees. Any questions on how we did that one? I see a few people still writing, so we'll wait a moment. Everybody have it? I do not like that problem. And I'm the only teacher for this class, so I can delete it. Don't worry, we're going to need a couple more too. This next one is somewhat important because this relates to the project. So in a certain state's lottery, 48 balls numbered 1 through 48 are placed in a machine, and 6 of them are drawn at random. If the 6 numbers drawn match the numbers that a player had chosen, the player wins $1 million. In this lottery, the order the numbers are drawn doesn't matter. Compute the probability that you will win the $1 million prize if you purchase a single ticket. So what we need to figure out is how many different tickets are there. And it tells us the order of the numbers drawn doesn't matter. The order doesn't matter. So I have 48 numbers and I'm choosing 6 of them. So it's a combination. So same process, 48 factorial over 48 minus 6 factorial, 6 factorial. So this is 48 factorial over 42 factorial, 6 factorial, which is 48 times 47 times 46 times 45 times 44 times 43 times 42 factorial. 42 factorial times 6 times 5 times 4 times 3 times 2 times 1. Everybody okay with what I did there? And then since I have 42 factorial in the denominator and 42 factorial in the numerator, I can cancel them out. And this is 720. And 48 times 47 times 46 times 45 times 44 times 43 gives me a whole bunch. 88354888640. Divide that by 720. And I get 12,271,512. So that's how many combinations there are. How many winning tickets are there? How many winning ticket combinations are there? Only one way to get 6 out of 6, right? So the probability of getting the million is just 1 over 12,271,512. Somebody make note of that. We're going to need it later. Any questions on how we calculated that? And in case you're wondering, 1 divided by 12.271512. That's not right. 1 divided by 12.271512. This is equivalent to 0.000000081. Have a very good chance of winning. And considering, I think the current lottery is at 53, or did it go higher than that even? Don't play it. Wise decision. So somebody keep this written down somewhere where we can refer back to it, because we are going to need it. Any questions on this one? Yes, you have a question, or yes, you'll keep track of it for us. Okay. So now we're looking at the same lottery. Okay. So now it states in the state lottery from the previous example, if 5 of the 6 numbers drawn match the numbers that a player has chosen, the player wins a second prize of $1,000. Compute the probability that you will win the second prize if you purchase a single lottery ticket. So, how many combinations were there? Was it 12, 2, 7, 1, 5, 1, 2? Now, what we want to know is how many ways can we get 5 out of 6? Order doesn't matter. All right. 6 factorial. 6 minus 5 factorial, 5 factorial. 6 factorial over 1 factorial, 5 factorial. 1 factorial is just 1. 6 times 5 factorial over 5 factorial is 6. Now, here's the thing. We can get 5 of the 6 numbers 6 different ways. What about the 6th number, though? How many ways can I, how many options do I have for that 6th number and it not being a winning number? Go in the wrong direction. How many numbers are there total?
6.
No, total. How many possible lottery numbers are there? No, not combination, just numbers. It's 1 through 48, right? So there's 48 numbers. 6 of them are winning numbers, right? So how many are not winning numbers? 42. So I can get 5 winning numbers 6 different ways. And the 6th number cannot be a winning number, so it can't be any of those 6. So it has to be one of the other 42. So we just take 6 times 42, which is what? 252. So our probability is 252 over 122711512. And again, somebody keep track of this. We're going to need it shortly. Any questions on that? Again, both of those examples will weigh heavily into the project, and so will the one we do later, referring back to them. Okay, so compute the probability of randomly drawing 5 cards from a deck and getting exactly 1/8. So the first thing we need to know is, well, actually, we can do this way. I can get an ace on the first card and not an ace, not an ace, not an ace, not an ace. Or I can get an ace on the second card. Or I can get an ace on the third card. N stands for not an ace. Or I can get an ace on the fourth card. Or I can get an ace on the fifth card. That's all my possible ways to do this, right? Everybody still with me? So let's look at this top one here. What's the probability that the first card is an ace? How many aces are there? How many cards are there? Okay. Now that I've gotten an ace, what's the probability that the next card won't be an ace? Well, how many non-aces are there? 40, how many? 48. How many cards are left? 51. Okay, now, third card. What's the probability it's not an ace? How many non-aces are left?
I'm sorry.
If we had 48, we took one of them out. How many are left? 47. And how many cards are left now that we've taken 2 out? 50. You had the right number, just in the wrong place. Okay, what about the next one? What's the probability of it not being an ace? 46 out of 49. And the last one? 45 out of 48. Now, looking at this is 4 times 48 times 47 times 46 times 45. And I'm doing this for a reason, you'll see. Over 52 times 51 times 50 times 49 times 48. Okay? And we won't even calculate it yet, because I want to go down to this last one here. What's the probability the first card is not an ace? Well, how many non-aces are there? New deck, 48 out of 52, right? What about the next card being not an ace?
And you said you drew one already?
Yeah, I drew one of first non-ace. 47 over 51. Then what?
46.
Over 50. And then what? Over 49. And then the last one is an ace. Four out of 48. Very good. So notice, that's the same. Notice, multiplication is commutative. I can bring this to the front. Then it would be the same as well. So all of these, each individual way you can do this has the same probability, which means all I have to do is calculate this one and multiply it by 5. So doing that, I have 4 times 48 times 47 times 46 times 45. Oh, I'm going to go ahead and, no. I have 186,79680 over 2 times 51 times 50 times 49 times 48. 311,875,200, and then we're going to multiply that by 5. So we have 186,79680 times 5 divided by 311,875,200. And I get 0.29947366. Or roughly, although we don't usually talk about percentages when we're talking about probability, roughly a 36% or 30% chance of getting just 1/8. Any questions on how we calculated that? I will reiterate at this point that if it's not on the homework, it won't be on the test. And I don't believe there's a problem like that on the homework. Any questions? Okay. Not going to deal with that one. It's worked pretty much the same, but it's a little bit different. So let's look at this one. How many people do they have? 2, 4, 6, 8, 10, 12, 14, 16. Probably not going to work. How many do we have online? That might be a good test. So suppose we have 3 people in a room. What is the probability that there is at least one shared birthday among these 3 people? And we're talking month and day, not year. So here's how we would approach this. Looking at the first person, what is the probability that their birthday will be the same as their birthday? 1. 1. Probability your birthday is 1. Unless you can change your birthday. Now, what's the probability the second person has the same birthday as the first person? 1 in 365. We don't do leap years here. Now, what's the probability that the second person has the same birthday as one of the other 2 people? Well, how many possible outcomes will be a positive result? How many different birthdays are we talking about? 2. How many days in a year? So we get 2 over some big number. 365, 360. Oh, not that big. 133,225. Okay. Any questions on how that works? I'm not going to deal with 5. But I do want to do this. This is interesting. And it's something you can do if you're ever at a party with 30 or more people. And we're going to try it. We're right on the edge of 30 if everybody online responds. And there's 17 in here and 13 online. So we'll see if this works. Suppose 30 people are in a room. What is the probability that there is at least one shared birthday among these people? So those of you online, please participate in this, or we will not, definitely will not meet the standard. So my first question, how many birthdays do we have in January? What day? 24th? 4th? 11th? Is that everybody in class? Anybody online? I got a 13th. Any other online? So it didn't work. Let's try February. Any February birthdays in here? 4th? 18th? 6th? Online? 11th and 13th. Close. Is that everybody? How about March? Anybody online? 4th. It took to November in a previous class. They have twice as many people. How about April? No April birthdays, only one online, so almost an April Fool. Oh, and an April 20th, but can we just erase the 0? How about May? No May in class. Any Mays online? Nope. Okay, how about June? And I'm 13th. No online June birthdays? Close. How about July? Any Julys online? Just the one? How about August? Anybody online? I'm looking bad here.
31st.
Doesn't help me. How about September? Any September babies? Any September babies online? I don't think it's going to work. How about October? 5th? Any October online? You got a bad feeling. How about November?
3rd.
November 3rd? Oh, we got 2 online. 6th and 15th. Dang it.
Oh, they should have birthday 15 and 15 online.
Was there 15 and 15?
Yeah, 2 years ago.
Yeah. Ah, there we go. See, it worked. And we only had 30 people. So that's a little parlor trick you can do. I would say bet your friends at a party if you have 30 or more people, but I'm not allowed to say that. So, because you think it's going to be astronomical, but the adding probabilities, eventually it runs. How does that get blue? It runs about 0.70 probability. And I've been doing this same thing pretty much every time I've taught this class, sometimes multiple classes, and it's only not worked twice. Okay, so this is the one where I'm going to need those numbers here in a minute. So the last concept, and again, this will tie into the project, is called the expected value. The expected value is the average gain or loss of an event if the procedure is repeated many times. We compute the expected value by multiplying each outcome by the probability of that outcome and then adding up the products. So as I believe I mentioned, we're going to talk about gambling in here. So here we're talking about roulette. In case you're not familiar, the roulette wheel has 38 spaces, 18 red, 18 black, and 2 green. We spin it. In one possible bet, the player bets $1 on a single number. There are the numbers 1 through 36, 0, and 0, 0. If the number is spun on the wheel, then they receive $36, their original dollar plus 35. Otherwise, they lose their dollar. On average, how much money should a player expect to win or lose if they play the game repeatedly? So, first thing we need is the probability of winning. There's 38 numbers. We're going to pick one of them. So what's the probability of winning? 1 out of 38. Which means what's the probability of losing? 37 out of 38. Now, if you win, what is your net gain?
35.
Your gain is $35, right? If you lose, what is your loss? So -1. So we have the probabilities, we have the outcomes, multiply probability times the outcome. 35 out of 38. Negative 37 out of 38. Add them together. -2 out of 38. Which is approximately -5 cents. So what this is saying is if you were to play roulette 1,000,000 times, betting $1 at a time, you can expect to be out $50,000. You won't get your money back. Now that's on average multiple times. So now you see why all them casinos have big buildings and shiny and all the bright lights, because they can afford the power bill. A nickel for every person that plays that, every time they play it. And even the almost sure thing bet, which is black or red, you still have a loss. Because you think, oh, it's 50-50, but it's not, because there's 2 green numbers. So it's a little less than 50. That's the house advantage. And that brings us back to what I've been talking about all along. Going back to that state lottery. There's 2 things left. In a certain state's lottery, 48 balls numbered 1 through 48 are placed in the machine, and 6 of them are drawn at random. If the 6 numbers drawn match the numbers that a player has chosen, the player wins $1 million. If they match 5 numbers, they win $1,000. It costs $1 to buy a ticket. Find the expected value. So I need the probability of winning it. Does anybody remember what the denominator was? 12 million and something. 5 what? 5/4? 5/12. Okay, and then we calculate the probability of winning 1,000. I remember that part, and now we know what this part is. So we have a total of 12,271,512 possible tickets, right? And looking at this, I have 1 plus 252. I have 253 winning tickets. Everybody see that? So how many losing tickets do I have? Well, we simply subtract. Did I subtract that right? So the probability of losing is 12,271,259 over 12,271,512. Everybody still with me? So we have a probability of winning $1 million, probability of winning $1,000, and probability of losing. So what's the outcome if we win $1 million? What's the net gain? $511.
Sorry.
All right. 999,999 because we paid the $1 in. And here it's simply what? 999. And here it's -1. Okay. And this is just like your project, except there's more options. There's more ways to win than just 2. And we'll go into detail on that on Tuesday. So now I just multiply probability times the net gain. And here's where I say this every semester and I still get people doing it. The best way to do this is just leave the denominator. Because when you add them all up, first of all, you have the same denominator, so we really only have to add numerators. I'm getting to the last one. But also, do the math here, and you're going to get less than a cent, I believe. Maybe a penny. But it's going to be with lots of decimal places, and it's going to throw your total thing off. So just leave it as a fraction, and then add them. So 252 times 999. And this is 251,748 over 12,271, 512. And now, just to add these up, well, we know what our denominator is. 12,271, 512. And our numerator is 999,999 plus 251,748. And remember, the last one is negative, minus 12271, 259. And I get negative 11019512. Then do my division. 12,271, 512. And I get roughly 90 cents. Oops. And it's negative. So what does this mean? From a pure mathematical standpoint, if you were to buy all 12,271,259 tickets, you would lose 90% of your money. You're going to lose roughly 90 cents of every dollar you put in. You'd win all the prizes, but they're not big enough to make up for what you would spend. And we're actually going to look at that when we do the project. Any questions on how we did that? Okay, and then we have the last one. Another expected value. This is real world situation here. Not that a lot of you are not real world, but a 40-year-old man in the U.S. has a 0.242% risk of dying during the next year. They have people that sit in offices and calculate this stuff. An insurance company charges $275 for a life insurance policy that pays a $100,000 death benefit. What is the expected value for the person buying the insurance? So, what is the probability that a 40-year-old man is going to die? Now, this is a percentage. So we need to turn it to a decimal, 0.00242. Okay? Now, he has two choices. He's going to live or he's going to die. So if the probability of dying is 0.00242, the probability of living would be 1 minus 0.00242, which is 0.99758. Okay? So if he dies, what is the net gain? Well, you're going to get his survivors would get $100,000, but then he paid in that $275. So the net gain is $99,725. Okay? And then, of course, if he lives, he's out the $275. So now, again, multiply probability times the net gain. Probability times net gain. And what do we get? So I have 0.00 242 times 99,725. That gives me $241.33. Then I have 0.99758 times 275. That means you're going to be out $274.33. So, on average, the person buying this insurance is going to beat out $33. And this is how insurance companies make their money. They have, I believe the term is an actuary. He calculates the probability of different people dying. They create a table. And you can use that information to get an idea of how much to charge. You know, if they wanted to make $33 on average for everybody that bought that insurance policy, this would be the rate they would charge, $275. They wanted to make more, maybe they charge $300. So any questions on how this works? So next week on Tuesday, we'll look at the project. I'm actually going to go through the process of calculating the probabilities. This is this probability times this net gain. And the next Thursday, we will do the study guide, which you may have noticed is the homework question. And then the following week, which is what? 26th, the week of the 25th, 26th, whatever the Monday is. That'll be our test week. You can take it either Tuesday or Thursday. If you take it Tuesday, you don't have to come Thursday. If you plan on taking it Thursday, you don't have to come Tuesday, but please don't get sick on Wednesday and not be able to come in, because then we have trouble. So any questions on anything? On